André-Marie Ampère, the unsung pioneer of electrodynamics. Intro. Every time you use your phone, start your car, or flip a light switch, you're commanding a fundamental force of nature. It's a force so woven into our reality that we barely notice it. For us, electromagnetism is nothing special anymore. We find it wherever metals are sorted and lifted. But it also performs other tasks. For example, electromagnets are responsible for the friction-free floating of the Trans-Rapid Magnetic Monorail. Yet, our entire digital world and the very pulse of modern life were all kick-started by the minds of early electricity heroes. For one such man, André-Marie Ampère, the story of this scientific breakthrough doesn't start in some pristine laboratory. It doesn't begin with a flash of inspiration under an apple tree. It begins when, in a revolutionary chaos, his father lost his life. This is the story of how a man who lost everything to political terror, a man shattered by grief, channeled his immense personal tragedy into one of the most important discoveries in physics. This is the story of André-Marie Ampère, one of the founding fathers of the science of electrodynamics. And it's the story of how his very advanced vision of reality remains one of science's greatest what-if. Section 1. The making of a mind. To understand the man, you have to understand the world that made him. André-Marie Ampère was born on January 22, 1775, in Palerme near Lyon, France, into the height of the French Enlightenment. This was an age of reason, of explosive curiosity, where the atheistic scholars started to see the universe not as some divine mystery, but as a grand puzzle, which could entirely be solved by the human mind. His father, a well-off silk merchant and a fan of the philosopher Jean-Jacques Rousseau, decided his son wouldn't have formal schooling. Instead of a rigid classroom, young André's world was his father's huge library. He was set free to forge his own path, most notably tearing through all 20 volumes of Diderot and D'Alembert's famous encyclopedia from A to Z. The boy was a prodigy. Before he could properly read, he was supposedly doing complex math with pebbles and breadcrumbs. By age 12, he was considered a mathematical genius, and at 13, he taught himself Latin just to read the works of giants like Euler and Bernoulli. He was a true polymath, consuming math and science, but also philosophy, history, and poetry with equal passion. But just as the Enlightenment was peaking, a shadow was falling over France. The ideals of liberty and reason were souring into the bloody extremism of the French Revolution. In 1789, the Bastille fell, and Ampère's world was changed forever. His father was called to be a local judge, a position that put him directly in the path of the coming storm. When the radical Jacobin faction seized power, his father was accused of being a monarchist and was sent to the guillotine in 1793. André-Marie was just 18. The execution of the father, who had so carefully nurtured his genius, left him shattered. He fell into a deep depression and abandoned his studies for nearly 18 months, completely lost in grief. The family's fortune was confiscated, leaving him suddenly penniless. To support himself, he started teaching mathematics, first privately and then in 1801 as a professor of physics and chemistry in the small town of Bourg-en-Bresse. Tragedy would continue to follow him. In 1799, he married Julie Caron, but just 4 years later, she died of tuberculosis, plunging him back into despair. A second marriage years later also ended unhappily. Yet, it was in the predictable, logical laws of math and physics that he would find his refuge. In 1802, he published an essay, Considerations on the Mathematical Theory of Gaming, which proved that a player would always be beaten by an opponent with much greater assets. This paper earned him notice among Parisian scientists, and he eventually rose through the academic ranks, becoming a professor at the prestigious École Polytechnique in 1809 without any formal qualifications. Section 2. The Spark from the North. Before the 1820s, electricity and magnetism were generally considered separate and unrelated phenomena. There were only small observations suggesting a possible connection, such as compass needles being affected by lightning. Both phenomena had been known since antiquity, but electricity was a strange fluid from early batteries, and magnetism was the property of lodestones that guided ships. They were two different chapters in the book of physics. In 1820, news arrived from Denmark that would set the scientific world on fire. A Danish physicist named Hans Christian Ørsted, while preparing for a lecture, noticed that a wire carrying an electric current made a nearby compass needle twitch. He'd stumbled onto a connection, proving for the first time that electricity could create magnetism. In September of that year, Ampere's friend, the physicist François Arago, demonstrated this bizarre new phenomenon in Paris. Ampère, known for his absent-mindedness and shyness, was in the audience and became a different man. He threw himself into a frenzy of experiments. He was so consumed by inspiration that, much like Mozart, who would famously jot down musical ideas on any available surface, Ampère was struck by a thought while walking in Paris. Legend has it that he pulled out a piece of chalk and, without thinking, scribbled his equations on the back of a horse-drawn carriage, which then promptly rode away, taking his fleeting genius with it. Less than a week after seeing the demonstration, he was presenting his own, more advanced findings to the Academy. To test his idea, he designed an electrodynamic balance. He set up two parallel wires, each hooked up to a battery. He passed a current through both in the same direction. The wires moved toward each other. Then, he reversed the current in one wire. They pushed apart. This was the birth of a new science. Ampère had demonstrated magnetic attraction and repulsion without a single magnet in sight. It was all electricity. He proved that electric currents were the true source of all magnetism and called this new field electrodynamics, the study of electricity in motion. Section 3. The language of force. By the way, Ampère had some views that seem unusual today, but in these times of initial exploration of electromagnetism were considered completely viable. Where electricity and magnetism seemed to many as two separate forces, Ampère saw something deeper. Along with Wilhelm Weber and other forward-thinking contemporaries of his time, he held a perspective that magnetic phenomena weren't truly separate from electric phenomena at all. Instead, what we perceive as magnetic interactions could be explained as manifestations of more fundamental electric charge interactions. Thus, no need for concepts like magnetic field, magnetic flux, even magnet. They all boil down to something more fundamental in light of unified theory of electrodynamics. Weber proposed that magnetic forces are actually electrical forces modified by relative motion and acceleration. Thus, no special formulas for so-called magnetic forces needed. What Ampère did separates a great experimenter from a true giant of physics. He wanted to translate this new physical reality into the pure, undeniable language of mathematics. The result was Ampère's force law, a single, powerful equation to calculate the force between two current-carrying wires. He also gave us the right-hand grip rule. When the thumb of the right hand points in the direction of the current, the fingers point in the direction of the magnetic field. What made Ampère's approach truly revolutionary was his insistence that we didn't need separate theories for electricity and magnetism. While many of his contemporaries were content to treat magnetic effects as a distinct force of nature, Ampère argued that everything we call magnetic could be reduced to the interactions of electric currents. In his vision, even permanent magnets weren't truly magnetic. They worked because of microscopic electric currents flowing within their structure. This unified view was remarkably ahead of its time, as it eliminated the need for concepts like magnetic fields or magnetic flux. Everything could be explained through electric charge interactions alone. This law laid the mathematical foundation for almost every piece of electrical technology to come. Electric motors, generators, and transformers all rely on the principles he uncovered. Every time you hear the whir of a motor, you're hearing an echo of Ampère's law. He was also a brilliant inventor. He created the solenoid, a coil of wire that acts just like a bar magnet when a current runs through it, the blueprint for the electromagnet. In a stroke of breathtaking foresight, he proposed that even permanent magnets worked because of tiny electrical currents circulating in every single molecule, what he called an electrodynamic molecule, the forerunner of the idea of the electron. He also developed one of the first instruments to measure current, later refined into the ammeter. The great James Clerk Maxwell, who would later build on Ampère's work, called him the Newton of electricity. Inspired by successful YouTube creators that make a lot of money from their channels, then, Matt Parr's Tube Mastery and Monetization course, as well as Tube Magic service, can save you a ton of time and effort. You're welcome to check out his channels, Make Money Matt and Matt Parr Course Reviews, to see for yourself what a ton of value he gives to the world and what money-making opportunities you might be missing out on. Feel free to check out the courses and software products and that are pointed out in the description. What if they turn out to be genuinely useful for you? Anyway, your support is the current that powers this channel. Now, back to the show. Section 4. The Vision and the What If. So, Ampère had laid out for the world the laws of electrodynamics. But the story doesn't end there. In fact, this is where it takes an unsuspected turn into one of the most fascinating what-if in the history of science. To understand this, we need to meet the other giant of 19th century physics, Michael Faraday. Faraday was a brilliant experimenter who thought in terms of invisible fields of force. He also entertained the idea of an ether, changing his mind on whether ether should be kept in the theory. Where Ampère saw forces acting directly between wires, Faraday imagined a wire creating a magnetic field, which then acted on the second wire. In the 1860s, James Clerk Maxwell took the work of both Ampère and Faraday and unified them into a single theory of electromagnetism. But, at the suggestion of William Thomson, he leaned more towards Faraday's theories and overlooked some of the Ampère's conjectures and math, preferring to develop the new math himself. In the sophisticated form of quaternions, it proved to be cumbersome for his successors. Nonetheless, Maxwell's theory was a triumph, describing electricity, magnetism, and light as different aspects of one thing, the electromagnetic field. And, crucially, in Maxwell's framework, the electromagnetic waves are transverse. Think of shaking a rope up and down. The wave moves horizontally, but the rope moves vertically, perpendicular to the wave's travel. But here's the what-if. Ampère's original math was a force law, more general in some ways. It didn't explicitly rule out or forbid forces acting along the direction of the current. In principle, it could accommodate phenomena that were not just transverse, but also longitudinal, like a sound wave, which compresses and expands in the same direction it travels. When Maxwell synthesized his theory, he was heavily influenced by Faraday's field concept, so his formulation naturally highlighted the transverse waves that explained light. The other possibilities hinted at in Ampère's work were largely sidelined. But the question has lingered. Did we lose something in the translation? Physicists, including the later Russian scientist Gennady Nikolaev, have argued that a deeper look at Ampère's unfiltered work could point towards new ideas, suggesting Maxwell's elegant theory may have overlooked phenomena contained in Ampère's original vision. This isn't to say Maxwell was wrong. His theory is one of the most successful in all of science. But it could be just a small partial case of a much bigger reality. Science isn't always a straight line. Ampère laid down a rich foundation. Maxwell built a magnificent structure on it, but he didn't necessarily use every single stone that Ampère had quarried. Conclusion. André-Marie Ampère died on June 10, 1836, at the age of 61, on an official trip to Marseille. His health had failed, and he was beset by personal and financial struggles to the very end. He was buried in the family grave at Montmartre Cemetery in Paris, his monumental contributions not yet fully appreciated. He was, in many ways, an unsung hero of his own revolution. His legacy, however, is written into the language of science and the infrastructure of our world. At the First International Electrical Congress in Paris in 1881, where attractions included Edison's new light bulb and Siemens' electric tram, his name was immortalized. Alongside the volt for Alessandro Volta and the ohm for George Ohm, the fundamental unit of electric current was named the ampere. It is a fitting tribute. He was the first to truly define electric current and understand it as the prime mover of the magnetic universe. The story of André-Marie Ampère is the story of a tragic hero, a man who faced unimaginable loss, yet found the strength to decode a fundamental secret of the cosmos. He was a self-taught genius who, in a blaze of brilliance, laid the entire mathematical groundwork for our electric world. His laws govern the motors in our homes and the power grids connecting our cities. But his story is also a profound reminder of how science works. It's a story of individual genius, but also of a conversation across generations. It's a story of how elegant simplification can lead to immense progress, but also, perhaps, how some richness can be lost along the way. We live in the world Maxwell built on Ampère's foundation. But we are left to wonder about the other pargs, the other possibilities that might still lie dormant in the mind of the man who turned personal tragedy into a triumph that would, quite literally, power the future. All this was only made possible by the basic research done by André-Marie Ampère.